In today's lab, you played with two kinds of circuits, series and parallel, and tonight I'm going to talk about the physics behind both. So first, a series circuit. That's where there's only one path that the current can take. So only one path that our current can go around, or our electrons can flow through. And they have to go through both bulbs. If we were to take one bulb out of a series circuit, so if I suddenly removed R1, if I took it out, R2 would also go out, because then we would have broken the path from R1 to R2. Mathematically, in this circuit, if this battery has a voltage V, then this light bulb will get part of that voltage, let's call it V1, and light bulb R2 will get the second part of the voltage, V2. These two voltages will add to the original voltage of the battery, which is what this kind of torn up sentence is over here is trying to say. V1 plus V2 equals VBAT. So the voltage on the battery will get divided up between these two bulbs. And it's not necessarily divided evenly. It depends on the resistance of each bulb. And you can use V equals IR. You need to know the current across it and its resistance to find the voltage across it. Anytime we add a resistor in a series circuit, the overall resistance of the circuit changes. So each one of these resistors pushes back a little bit. If you imagine electrons going through, each resistor pushes back a little bit. That's what it means to resist, to push back. So it pushes back against the current a little bit. And the more resistors we put in, or the more light bulbs we put in, the more the resistance goes up. So in a series circuit, every time you add a resistor, equivalent resistance increases. Your overall circuit resistance increases. And that's going to be kind of the main takeaway of tonight's video, is showing you how to find equivalent resistance for both types of circuits. It's actually coming at the end though. I want to kind of talk through the physics of each circuit first. Even though the voltages add, each of these bulbs will get the same current. And that's because current isn't used up. The same number of electrons that go into this bulb have to come out. So how many ever electrons we put in the bulb have to come out of the bulb. They're not going to build up inside. So the current stays the same. So if this was I1, and this was I2, and this is I battery, they're all equal to each other in a series circuit. I1 plus I2, nope, not plus, whoops. I1 equals I2 equals IBAT. In a series circuit, the current is the same everywhere. So make sure you've got that, key points. In a series circuit, voltages add, right here. Current is the same everywhere. And if you remove one resistor in a series circuit, there is no longer a path, electricity will no longer flow through it. Voltages add, current's the same. If you remove a resistor or a light bulb, the whole circuit stops working. Okay? Those are the key points. Make sure you know that that is for a series circuit because it's different for a parallel circuit. Also, a little bit of analogy over here on the right. Imagine water flowing instead of electricity. Whenever you hit a resistor or a light bulb in a series circuit, it's kind of like you've squished in the space where the water flows, so you've made it a little harder to go through. And every time you squish it in, you make it harder for the water to go through the whole thing. And if we were to just completely remove this section, water wouldn't flow. In a parallel circuit, both of the resistors are connected independently to the battery. So imagine this is our battery here. Each one is independently connected to that battery, and so it gets the entire voltage of the battery. So the voltage drop across each bulb is the same. So if this bulb has a voltage drop V1, this one has V2, and this one has VBAT, voltage 1 equals voltage 2 equals voltage BAT. You got to remember that in a parallel circuit, it's the voltage that's the same everywhere, whereas in the series circuit, it's the current that's the same everywhere. They kind of do opposites. Same with current. Because when we get to this junction here, the current can either go down or it can go to the right, the current will split. And so if this bulb gets I1 and this bulb gets current 2, and over here we have the battery's current, or the current that initially came out of the battery, I1 plus I2 equals IBAT. So notice it's the opposite of a series circuit. In a series circuit, voltages add and current stays the same. In a parallel circuit, voltages are the same and current adds. And I've got the water analogy over here again. Imagine we have this much water, so this much current coming in, and then we split it apart the current over here plus the current over here must equal the initial current. And then at the end, it all comes back together. So whatever current leaves the battery going this way comes in back going this way. So they'll separate up here, and then they'll come back together down here. So whatever current leaves the battery goes into the battery. Current's not used up. All the electrons that leave it have to eventually come back to it. Now, about resistance. Every time we add another resistor, so if this is my circuit down here, every time I add another resistor, I give another path for the electricity to flow through. And every time I add another path, it gets easier to flow. No matter how big this new resistor is, even if it's 1,000,000 times bigger than all the other resistors on here, it will still make it easier for electricity to flow through the path because it has another lane. You can think of it as like the lanes at the supermarket. If you get in line, so here's one checkout counter. We get in line, we need to check out, and there's 20 people in front of us. If they open another line, no matter how slow this new checkout person is, this line will now move faster because we've given another path. So no matter how slow your new checkout person is, overall, everybody in the store will still get out faster because you've opened a new lane. Same thing with adding resistors in parallel. Every time you add one, you add a new lane for the electricity to go through, and so the equivalent resistance, every time you add a resistor, will always decrease. Resistors in parallel always decrease resistance. Okay, so key points. Voltage is the same everywhere in a parallel circuit. Current gets split up, but your total current leaves the battery and comes back to the battery. And all the current through the resistor add to give you the current that initially left the battery. So current adds, voltage is the same everywhere, and every time you add a resistor, you decrease resistance. Counterintuitive. And if we remove one bulb, the other one would stay lit. If we took out this one path for the water, the other one would still exist. All right? Now we're going to go over how to find equivalent resistance, which sounds very fancy, but equivalent resistance is just the total resistance in any circuit. So I'm going to show you how to find, given a circuit with certain resistors, the total amount of resistance supplied by that circuit. And that's what this next part's about. Now I want to show you how you actually calculate equivalent resistance, and this is what your lab conclusion was getting at. In a series circuit, we know that every resistor adds resistance. And in fact, what I just said is the same expression mathematically. The equivalent resistance in a series circuit, and I'm going to write this in the calculus form first for people who know what sums are, and then I'll show it in the algebra way. Equivalent resistance is simply the sum from I equals 1 to how many ever resistors you have of the resistances. So then in non-calculus form, you add resistor 1 plus resistor 2 plus resistor 3, and so on. How many ever resistors you have in series, you just add them together in a series circuit. For a parallel circuit, each resistor decreases resistance, which means there's an inverse relationship to total resistance and number of resistors, and we can express that mathematically. In a parallel circuit, equivalent resistance is the total of the inverse of all your resistors. The sum from 1 to how many ever resistors you have, and in algebra form, and then to get correct units, before I do algebra form, we're going to flip it back over. And I think this will make more sense in algebra form to everybody. So let's do a therefore. 1 over equivalent resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3, and so on, up to how many ever you have. Now, the first one makes sense. You just add them. The second one could be a little more complicated, so let's do a math example for both. Okay, let's say I have 3 resistors. R1, which maybe we will say is 3 ohms. R2, 5 ohms, and R3, 8 ohms. First up, we need to find the equivalent resistance in a series circuit. So if I were to arrange these, the battery in series look like this. You have R1, R2, R3. And since it's series, equivalent resistance is just R1 plus R2 plus R3, which is 3 ohms plus 5 ohms plus 8 ohms. And if we add those together, 16 ohms. So in a series circuit, they just add together. It's very simple. However, if we were to arrange these in a simple parallel circuit, our battery, first resistor, second resistor, third resistor, R1, R2, R3, the equivalent resistance, we have to, if we're looking for equivalent resistance, we're going to take the inverse of all the resistors and say it's the inverse of the equivalent resistance. So 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. And if we fill that in, 1 over equivalent resistance equals 1 over 3 ohms plus 1 over 5 ohms plus 1 over 8 ohms. And the only way to add those together is to find a common denominator. In this case, I don't see anything super obvious, but I could multiply simply all of them together and make their common denominator 120. So 1 over equivalent resistance would be, if I do 3 times 5 times 8, I get 120. And then the 2 that I had to multiply that by were 5 times 8, so I get 40 on top, plus 120, common denominator on the bottom, 24, plus 120 ohms, their common denominator. 3 times 5 is 15. Okay, so now we have 1 over the equivalent resistance would be 120 on bottom, 120 ohms. 40 plus 24 is 64, plus 15 is 79. And so our equivalent resistance, Req, because this is inverted, so now if I flip both over, it's 120 divided by 79 ohms. In this case, I need to grab a calculator to get that into a number that's actually usable, or about 1.52 ohms. Now notice that this is smaller than any of the initial resistors, which has to be true in a parallel circuit. Your final answer will always be smaller than any of the initial resistors, because adding a resistor in parallel will always reduce resistance. And that's how you find resistance in a series circuit and in a parallel circuit.